So hello everyone, this is lecture 19 for the mathematical physics, in which we were studying about the functional matrix, and we saw some questions related to functional matrix. Up to here we did. Now let's see some more questions. Means up to here we did. So if this type of matrix is given, means all entries are 1, then we need to show that e to the power a is equal to I3, that is identity matrix, a upon 3 exponential power 3 minus 1. We need to prove this. Okay, so let's see how can we do this. So we know the expansion of exponential x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So just remember, if this type of matrix is given, then you can try to multiply a square a and like that. Then let's see what is a square, a into a. So when you do that multiply, you will get 3 in all the entries. So that is nothing but 3a. So if you know what is a square is 3a, then you can find the a cube, that is a square multiply a. So 3a multiply a, that is 3a square, and again you will get 3 square a. So you can solve this, you will get this. And likewise for a4, like 3a multiply 3a, then 3 to the power 2a square, then 3 to the power 3a. So that's how you will get these powers. So now you can use this result. How? Now if exponential x is equal to this, then e to the power a will be 1 plus a square by 2, this. Okay, we know this. Now we need to prove this now. That's why we taken this left hand side. Now we will prove this equal to this. Okay, so this is this. Now what we will do, so I3 already we got. Now we can take a by 3 common here also to prove this. So after taking a by 3 common, we will see here remaining. Here it will be 3, here it will be 3 square, here it will be 3 cube, and that's how you will get the entries. Okay, now see, this is kind of exponential series, but there is no 1, so we will add 1 and minus 1. Then it will be 1 plus x square by 2 factorial plus x cube by 3 factorial. So it will be e to the power 3 and minus 1. So you will get something like this. Add 1 minus 1. Then I3 plus a by 3 e to the power 3 minus 1. So it is equal to right hand side. So we proved this. Now there is one more example like this. If a is given this matrix, and we need to find this 3 minus 2a square minus a cube minus 5a4 plus a6. Okay, so this kind of question are asked in the previous years. So how can you do that? Just try to multiply a and a. So what you will get minus identity matrix, minus of I means minus 1 0 0 1. So if you have the a square, then you can find the a cube. How? It will be a into a square, and a square is minus I, so ai will give you a, so it will be minus a. And a4, that a square, then minus I will give you I. For a6, you will be a square, so minus I will give you minus I. Now you can use these results and put them in this, and you will get the answer. Substitute this 3i plus 2i plus a minus 5i minus I, you will get a minus I. Okay, so just go with the question, means whatever it is asking, just solve it accordingly, you will get the answer. Now we need to find EKA for the same matrix. Okay, so we know what is exponential Ka, the expansion we know, 1 plus Ka by k square by 2 factorial, like that. Now we have the value of A, this matrix, and A square this, A cube is this, so we can substitute the values here. So let's see what we will get. After substituting, we will get this type of series, 1 plus Ka minus k square I by 2 factorial minus k cube by A by 3 factorial, and like that. So what you can do, you can take this one in one side and this odd terms in the one side. So we'll get this type of series, means taking I common, that will be 1 plus minus k square by 2 factorial minus plus k4 by 4 factorial, and like that. So you should just after seeing this series, you should know that it is the combination of sine and cos. Okay, that's why we are doing this. So it should be your intuition that you can see this results. Okay, so you can see these results. So we take the I common, we'll get this series, and take a common, then we'll get this series, is odd terms and the even terms. So this is nothing but cos k, and this is nothing but sin k. So it is I cos k, a sin k. So multiply with, we will get this, and here we get this, and after adding we get e to the k equal to this. So easy. Now just remember these results for matrix. A plus b square is a square plus b square, ab plus ba, and ab is not equal to ba in general. And e to the power a plus b, you can't write it as e to the power a, e to the power b in general. You can write this like that only when ab equal to ba. Only then you can write e to the power a plus b as ea and eb. Just remember these results. Now what is the main topic today is the rotational matrix. So we will cover this in the 2-3 lectures. So what is the meaning of rotational matrix? And in it we will study about the matrix operators and the linear transformations. Okay, so what are linear operators? So there is any operation O. If you apply this operation on A plus B matrix, and it will give you OA plus OB. And if you apply this on K, here K is any constant, scalar constant, then it will give you KOA. Okay, then you will call these operator as linear operator. A and B are numbers, functions, or vectors. They can be anything. Okay, now we can find if any matrix is linear operator or not. Okay, a matrix can also be an operator. You know this from the quantum mechanics that M is nothing but, means a matrix is nothing but an operator. You can operate M on R1 plus R2. Okay, they can be any vectors. So if you apply on R1 plus R2, then it will give you MR1 plus MR2, and if you apply on MKR, this is R, then you will get the KMR. Okay, so we will call this matrix as linear operator. Okay, just remember this. This was the definition how you can call some matrix a linear operator. Okay, now consider some equations. There are some coordinates x and y, and you will get capital X by operating these xy, ax plus by, and you will get y equal to cx plus dy. Just consider these two equations. You can write them in a form of matrix, definitely. Here xy equal to, you can write a, b, c, d and xy. Okay, now see what you get here. This matrix is kinda operator, which operates on this column vector and give you xy. Okay, so that's how we can write this. We can write this capital R, this is small r, so r equal to mr. This is like we did in the orthogonal transformation and the unitary transformations. It is like that. So this matrix is working as a operator. For each xy we will get a capital Xy. For definitely different xy's we will get capital Xy. So this matrix is operating, means this is acting as operator. So hope the meaning of operation of matrix is clear to you. Now let's see some definitions. Each point of xy plane being moved to some other point, means this point, this coordinate is moved to some other capital Xy, means other coordinates, and origin is not moved. Origin is remains same, means frame is as it is where it is. So this is called mapping or transformation of plane into itself. When origin is not changing and these are just moving from one point to another point, then we call it as mapping or transformation of plane into itself. All the information of this transformation is contained in matrix M. So this transformation xy to capital Xy is contained in this matrix because we are operating this matrix. So that's why all the information of this transformation is containing in this matrix. So hope this is clear to you. Now let's see a practical example. What is the meaning of geometrical meaning of this transformation? So let's see this. Let's say this is xy plane and we have this small r vector. Its coordinates, here this point coordinate has xy, this point coordinate is xy. Now we rotated this vector by theta angle. Initially it was phi, now we rotated at theta angle. So we get some other coordinates capital Xy. So we transformed this coordinates to this coordinates. Okay, so this is this is active transformations, because all the information of xy is inside, means transformation is in the same plane, means now it is here, now it comes to here. So we call this active transformation after rotation, and origin is remaining same as it is where it was. So this is active transformation. Now there can be case second. Case second is like this. Now vector is as it is where it was. Okay, means initially the vector was here. Okay, now what we did, initially the vector was here. Now we rotated this whole plane, xy plane. It came to here. This vector is here. Initially the angle was this phi. Now we rotated this whole plane by theta angle. Now it is x, it is y, and it is remaining same. Now initially coordinate was r, and now its coordinates are r dash. Means this vector r, initially it was r, in the second frame, that is y dash x dash. Now coordinates are r dash. So vector is as it is, but its coordinates are changed. So we call this as passive transformation. Okay, passive transformation, and origin is still as it is where it was. So here we have two sets of coordinate axes, xy and x dash y dash, and one vector, means vector is same. Now xy component of vector in xy plane and x dash y dash are component of vector in x dash y dash plane. This is called passive transformation. So hope this is clear to you that what is active transformation. Means here the vector is rotated, but here vector is remaining as it is where it was, and the whole frame is rotating. So let's see some things. What if this transformation is orthogonal? Then the length means this is actually orthogonal. Why? Because you can see that this length of the vector is remaining same. Here it is same, here it is same, and here also length is this. After rotating, length is remaining same. So it preserves the length of a vector. Means after transformation capital R, the magnitude of R equal to small r, and r dash is equal to small r. Okay, so we can see that length is remaining same. So what is the length of this vector? If it is xy, then root x square plus y square will give you the length, and this will give you capital X, root x square plus y square. Here it is x square plus y square equal to x dash square plus y dash square. So I just write it this here. Length should be equal. So we write this is capital X square, capital Y square, small x square plus y square, and x dash square plus y dash square equal to x square plus y square. And we know what is this x dash y dash equal to after converting this xy to this, and this matrix is operating. Now we are finding that if this matrix is orthogonal or not. We are just verifying this. Okay, we are just verifying that this rotation is orthogonal transformation or not. So how can we verify? Now we know what is x and y, means x dash and y dash. Let's take the left hand side. Means this is the condition for the orthogonal matrix. Now we will verify if LHS equal to RHS. So we taken this x dash square plus y dash square, and we know what is x dash. X dash equal to ax plus by ka whole square, and y dash equal to cx plus dy ka whole square. So after solving this, we get this equation. Now if it is orthogonal, then a square plus c square should be 1, b square plus d square should be 1, and this should be 0. Only then we will get x square plus y square. So this should be the condition. Okay, so let's see. Now take this matrix M and take the transpose, and this is the condition for the orthogonal matrix. If it came out to be identity matrix, then we call this as orthogonal matrix. So let's multiply, we'll get this. Now put a square plus b square here. Now okay, so you see this condition. Means we know this is M matrix. We take the transpose of this and multiply it with itself. Means this is the transpose and this is this. First we take the M transpose. This came out to be this, and then we take the M transpose M, multiply this with this, we'll get this. And here you can see a square plus c square is 1, so we can substitute 1. ABCD is 0, and this ABCD is 0, and b square plus d square is 0 again. So M transpose M came out to be this identity matrix. So from this we can conclude that M transpose is nothing but inverse of M. Okay, only then we will get I. So if this condition satisfies, we know that this is the condition of orthogonal matrix. So we call this M matrix as orthogonal matrix. So this is nothing but orthogonal transformation, rotational transformation, we can call that orthogonal also. So we can verify this. Determinant of MT M is 1 definitely, because this is identity matrix from here, and this can be written as determinant of MT, determinant of M. This is equal to M transpose equal to M for determinant, and then determinant M can be plus minus 1, and this is the condition for orthogonal matrix. You know that the determinant is always plus minus 1 for unitary matrix or orthogonal matrix. Now there is a type of question which can be asked from this. Let's see what is this. For the case first, for this first, the vector was here, so components can be written as x equal to r cos phi, y can be written as r sin phi. So let's write them. X equal to r cos phi, y equal to r sin phi. Now what about the capital XY after transformation, after rotation? Now it is theta plus phi. So x can be written as capital R cos theta plus phi, and y equal to capital R sin theta plus phi. So we write them like this. Now let's expand. R cos x plus y is nothing but cos x cos y minus sin x sin y. So we multiplied this, x equal to this. Now from here r cos phi is x. So we substituted x cos theta minus y sin theta. So capital X came out to be this. And likewise we will solve for the y. This is sin x plus y equal to sin x cos y plus cos x sin y. Then substitute the value of xy from here, you will get this, x sin theta plus y cos theta. Now we have these equations. Now we can write them in the form of matrix definitely. Capital XY equal to cos theta minus sin theta cos theta, then xy. Now see, we call this as the orthogonal transformation, and we get the type of this type of situation. Now we transforming this to this using this operator matrix, and this matrix is definitely orthogonal. Okay, we already proved this. Now the case second, the passive transformation, where the frame is rotating. So initially the angle was phi and the coordinates were same, r cos phi, r sin phi. Initially coordinate was this. Now the frame is rotated by theta angle. Now this angle remaining is phi minus theta, phi minus theta. So the next angles will be r cos phi minus theta, y dash will be r sin phi minus theta. Now applying the means their identity, cos x minus y is nothing but cos x cos y plus sin x sin y, and sin x y is nothing but sin x cos y minus cos x sin y. So after substituting the values, we will get this type of situation. X dash will be, means using this and expansion, we will get x dash equal to this, y dash equal to this. Now this also can be written in the form of matrix, x dash y dash, then this cos theta sin theta, then minus sin theta cos theta xy. So this is also a transformation. This is orthogonal matrix, and you can see that this matrix and this matrix are inverse of each other. Okay, or we can say that these are nothing but orthogonal, means they are transpose of each other, and they are orthogonal matrix definitely. Now why they are transpose or inverse of each other? Because we can see when this vector, let's say this frame is rotating anti-clockwise in this direction, then you will see this vector is moving in this direction, clockwise direction, and here we are taking the anti-clockwise direction. Means here when this frame is rotating, then this vector is going in this direction, and these both conditions are opposite, but here we take the same anti-clockwise rotation for the vector and for the axis also. That's why we are getting these two inverse, okay, inverse of each other. So in the next lecture we will discuss more about these and see some examples and what kind of questions can be asked. So okay, thank you.